So many of you might know Bob Cobb. So he's the advisor for me and Alex. Although Bob is not here today, so he helped us a lot in terms of preparing this workshop and some acknowledgement, right? So are we really thankful for Palsy and Juliet to support us to doing this kind of workshop and also lastly, PaleoSTEHM project is kind of the project who support me and Alex to develop some spatial temporal hierarchical modeling tools for everybody to use. Okay, so lastly, this workshop will be recorded and we will try to make the recording available after this workshop so you can go back anytime you like. Okay, so let's kick off. So if you have any questions, just type in the chat, so I will try my best to answer those. So Alex, if you see those chat in the bar which I didn't notice, please let me know. So some of the background things, so why we are interested in paleo sea level spatial temporal hierarchical modeling, because we see this kind of environmental change from the ice core, and we see this kind of unprecedented CO2 level in the atmosphere. We want to know how our environment react to the climate change. So we want to get some information from the past. So if we look at the last 100 years of sea level record, we see that because of the global warming, the external forcing, we saw the accelerated sea level rise rates globally. But without this kind of satellite modern tide gauge record, we cannot really understand what's going on in the past and what's going on in the long-term future. A typical example is by Andrea Dutton's 2015 paper is that, like, we know the atmospheric CO2 is rising really quickly, but how does this CO2 will contribute to our sea level rise in the future? We can compare this in the geological past, like MIS 5e, MIS 11. Although it shows like we know really well with what's going on here, but actually, I know many of you are doing paleo sea level research. How much sea level rise in the past is still an open question to some extent. So to answer this question, we really need more types of records, what we call geological records. If you think about sea level problem, other than satellite altimetry and tide gauge data, which covers like 100, 200 years, if we want to go back in time, we really need more types of data, like archaeology data, macroato, so much. And if you go further back in time, you have sedimentary records, coral reefs, and other types of geomorphological indicators. And if you want even further in time, you might want to do some deep sea drilling with some ocean isotope analysis. Okay, so I know many of you is doing sea level research. So maybe like if everyone can type a little bit, like 1 or 2 words of who are you, like what's your study area, so we can have a better idea like what kind of variety we have here today. So maybe like let's type something in the chat bar. Is that possible? So who are you? What kind of research, 1 or 2 words you are doing? What kind of background you have, so we can have a really better idea of everyone. So I encourage you to type something, okay? To type something in the chat bar, please. Okay, so while you are typing, I'll try to continue. Okay, so but please type what's your background in chat bar, so we will better identify everybody's expertise. So here is a typical example, like how do you reconstruct sea level in the past. So if you see the figure on the left hand side, it's a cartoon showing you sea level at 21,000 years ago, which is what we call last glacial maximum, when global sea level was much lower than present day. You see some coral reef living here. Whoops. let me just draw something. You see some coral reef living here, and when we move to present day, we see sea level rise due to the ice melt, and this coral becomes a coral reefs, which can tell us a little bit about past sea level. So now, if we want to understand past sea level, we need some deep ocean drilling. So you see this boat here, you do some ocean drilling, you get some coral reef sample and get back to the lab. And in this lab, we found this coral sample, right? At a modern elevation of 120 meters below sea level. And from the lab analysis, we see we can identify what types of coral it is. For example, a specific type of coral called Aquara pomata, which is live 0.25 meter below sea level. So we can kind of infer this paleo sea level because we know that this coral reef this record is collected from 120 meter below sea level, and you have a range of 0.25 meter. So we can kind of reconstruct sea level in the past using this geological reconstruction method. So coral reef is definitely not the only record. So there are many records. For example, if you see here, like there are so much records. There are coral macroatolls. There are Roman fish tanks, some archaeology records as well. And all of them are geological records, right? For any geological record, we need to understand how old are they, right? So there are many types of geochronology technologies. Something called radiocarbon, uranium series dating, and OSL dating. So I think some of you might know this much better than me. So if we can reconstruct one sea level record, what can we have? We have a mean value. We have some chronology uncertainty expressed in the x-axis. We have some sea level reconstruction uncertainty in the y-axis, and we usually represent those as a box in our community. And here's an example by Tam et al. 2018. You can see that by reconstructing sea level in the past by a lot of records here, you can have a lot of reconstruction, and you can kind of understand how sea level changed in the past. Reconstructing sea level in the past is really challenging task because we have so much types of proxies, we have so much types of chronologies. All of them are contributing to different level of uncertainty, and usually data are really sparse and unevenly distributed in both in space and time. If you can see this figure on the right-hand side, there's a paper by Jennifer Walker, 2021. So you can see that although we are going to like Common Era last 2,000 to 3,000 years, we don't have too much sea level across the world. Most of them are North America and Europe. And I know there are a lot of data in Asia, in South Asia and China here now, but like generally they are much less compared to Europe data and North America. You can see that this data is really noisy in terms of temporally. You see them, some of them are falling, some of them are rising. So, and one more complexity is that the proxy data is really noisy. It's not like the modern instrumental data that was give you really accurate measurement. Proxy data is really noisy because their relationship between the proxy basically means you have something that can covariate with the target value, but you don't know how, right? For example, coral reef can change with sea level, but you don't know how. You do have that living depth, coral living depth you have to infer, which is what we call noisy. Okay, so the last complexity, maybe the most annoying one, is like radiometric based chronology and some proxy data can produce really complicated uncertainty distributions, which we are hard to deal with. Okay, so thanks for all of you to do some self-introductions are really great. We see some archaeology here, Holocene sea level, sea level in the past. Yeah, snow glaciers, that's really nice. So yeah, we do have like most really broad variety here, but I think many of you are really kind of familiar with like field reconstruction, and some of them you are really interested in numerical modeling. But today we're mostly talk about statistical modeling. Okay, so let's move on. So we talk about like we have this kind of noisy data, but the goal here today is hopefully today and tomorrow is we can try to extract a spatially uniform, what we call global mean sea level from this noisy data. And we can use this global mean sea level reconstruction to do some analysis, right? To do some analysis of maybe some human contribution to climate change, sea level change, and we want to do some analysis on how sea level change in different space. Okay, so that's our goal. So